All right, welcome back. So, in the first half of this lecture, we derived Euler's equations. So those are the equations of motion for a spacecraft, which is right there. They are spacecraft which doesn't have any cross inertial terms, two planes of symmetry. Well, yes, two planes of symmetry. In this lecture, in this half of the lecture, I should say, we are going to be studying what happens in the axisymmetric case. And by axisymmetric, I don't mean it's actually, is symmetric about an axis. I mean it has two planes of symmetry. And in those two planes of symmetry, so there's no cross terms if there's two planes of symmetry, then the Ix and the Iy principal moments of inertia are the same. So Ix equals Iy. Right, this is the case where you've got, say, a spacecraft that looks like this. Well, that's actually not a good one. It's too much symmetry. So take a spacecraft look like that, it has two planes of symmetry. Well, if I draw it like this. But Ix does not equal Iy. So we're going to consider instead ones that, well, they can still be flat, so let's make them flat. Ones that look more like that. Or, if we prefer, like that. That one is a truly axisymmetric one. Right. But this will be either case. Ix equals Iy for that one, and Ix equals Iy for that one. We're also going to be talking about the case where there's no torque, torque-free motion. Right? If you have torque, right, you want to control your spacecraft with torque, right, you can add them in here, but we're not going to be talking about that in this lecture. This can come from gravity gradient, it can come from thrusters, it can come from reaction wheels, it can come from CMGs, it can come from torquers, wherever it comes from, doesn't matter. And it especially doesn't matter because we're not going to be considering it. However, these are usually, I should mention, expressed in body fixed frame. Right. So let's get to the point then. So axisymmetric spacecraft, right? So axisymmetric, so here's a good axisymmetric spacecraft here on the left, right? No, it's not much of a spacecraft, but, it sort of looks like one. And that means, well, it's not actually symmetric about the axis completely, but it has this important component that Ix equals Iy, right? So it doesn't matter if this is x or this is x, the geometry doesn't change. And that's what we mean by axisymmetric. So if we swap the x and y axes, well, you can't really swap them because they wouldn't be a right-hand coordinate system. But if you swap them, right, you made at yx, it wouldn't change the moment of inertia tensor. And that's what we're looking at. Compare that, of course, to here's Starlink, right? That's I like bringing in Starlink because it's new and interesting, which is, even if we just ignored this like solar thing right here, the solar panel, then it would not be axisymmetric, right? Because we made that the x-axis, versus if we made that the x-axis, the moment of inertia tensor would change, right? Would change the x, y, and y would swap. I just put down a inertia tensor for the Starlink, just, guessing, right? Has a very, assuming this is the z-axis, let's say I should make this right-handed. If I made that z, then where should I make that? Then, yeah, okay. Then I can make this my x. Oops, wrong side. X, and I can make that my y. And in this case, right, it has very small principal moment about z. No, so actually, I don't want it to get very far from the z direction. So actually, this should be, I'm getting it all wrong. So its largest component is about the x-axis, so I should make that x. And then I'll make the y here. Let's see. The z direction, it has the smallest measure about z, so this should be z. So it's z because it doesn't go very far in that direction. And y, it has a large, or the distance from the largest is y, so that sort of lines up. Of course, that's not a right-handed coordinate system, so let me think. X, y. Oh no, that is a right-handed coordinate system. Right? Okay. So maybe I exaggerated the 1 here. Maybe I should make that 2 or something. I don't know. Anyway, it's just a guess. I don't have the actual specs on these spacecraft, so I can't really say. And of course, the solar panel would give us cross products of inertia anyway. So. But just to show you, this is not an axisymmetric spacecraft because, right, that length is larger than that length, and this is. Here's another axisymmetric, a real axisymmetric spacecraft near Shoemaker, and you can see that these are approximately equal, right? So that's an axisymmetric spacecraft. And so that indicates, by the way, that that's the z direction. Which is the x, which is the y, doesn't matter. One of those could be that. Could also be that. Except I draw it badly. Y. All right. So the special case of axisymmetric spacecraft is very important for us. We try and make our spacecraft axisymmetric as much as possible because it does simplify the dynamics quite substantially, right? And so if we take our Euler's equations and we focus on the third one, right? Remember there were 3 of them, right? A little bit farther back, right? There are 3 equations of motion if we took sort of just the scalar versions, right? Not the vector version. If we look at this one, right? The special case of Ix equals Yy means that this goes to 0, right? And so if we look at that third equation of motion, right, Ix equals Iy means that that part goes to 0. And so 0 times anything is 0. And so the right-hand side is all just 0. And so the important part is that the omega dot z, that's the component of the rotation vector in the z direction, and assuming that's the z direction, could be down, but looks like we've drawn it up, right? The component of rotation, if this is our rotation vector, omega, the component in the z direction, omega z, is constant. Right? It's a constant. So now, if we write out our omega constant, if we write out our remaining equations of motion, right? Well, omega dot's not 0. Omega z is not 0, right? It's constant, right? But it doesn't change with time, and so we can pull it out of the equations, and we get something which, while it was originally nonlinear, right? These are nonlinear. There's cross products here. Not linear in the state variables, which are omega x, omega y, and omega z. Now, because we've been able to eliminate one of our state variables, well, we didn't eliminate it, we solved for it. It's known. It doesn't change with time. We can pull that out in these coefficients. There's only 2 of them. There's this one and this one. Those are constant, right? And now the dynamics become linear in the remaining state variables, which are omega x and omega y. Remaining state variables. So we have a second order linear ordinary differential equation. Linear ODE. Second order, because there are two states and only one derivative in each state. So I emphasize that the rest of this lecture applies only to the case of axisymmetric spacecraft. Only Ix equals Iy. In the next lecture, the last lecture, we'll consider the case where they're not equal. But in this lecture, the rest of it, we consider this case. Right. So in this case, the equations of motion become very simple. Right? We just define those two coefficients, and in fact, they're the same coefficient. If we go back to the equation, they're the same coefficient, right? This equals that. And so we'll just call those two coefficients lambda, right? And we get a very simple equation. Omega dot equals 0, negative lambda, 0, omega. Right. And, no, I think I've made a mistake. Oh, no, I didn't make a mistake. Yeah, so they're not actually equal to each other. This is Ix minus Iz, and this is Iz minus Iy. Those are the same, right? So this is, one of these is negative. We'll call that one negative, lambda. So, oh no, we're calling this one negative. Sorry. Okay, so anyway, we have two equations of motion, very simple, scalars. We can combine them, right? We can just plug omega y. Take the second derivative, omega dot x equals, take its second derivative, equals negative lambda. Just take the derivative of this one, negative lambda omega dot y, and we plug in there for omega dot y. That's equal to negative omega squared omega x. So omega double dot x equals negative lambda squared omega dot x. So we get one equations of motion decoupled from all the others for omega x, right? And hopefully, just going out on a limb here, you've at some point, and I usually ask this during class, right, just to make sure, that you've seen the solution to a scalar linear ODE. Now, and in particular this one. So hopefully you know that its analytic solution is this, right? If you don't believe me, you can, right, you can verify this by taking the derivative, right, the second order derivative of omega x, and then this becomes sine, negative sine, and then it becomes, again, when you take its derivative again, or lambda, negative lambda squared cosine, right? So you get back to the original form, and you can just expand that out and prove to yourself that omega double dot x equals negative lambda squared omega x if you need to. Okay. So, okay, all right. So what we have here then is a closed form solution for omega x. Well, what about this omega dot x not here? Well, to get rid of that, we can notice that, right, omega y equals negative 1 over a lambda of omega dot x. And so if we take the initial condition on y, we can solve or eliminate for the initial condition on omega dot x, right? So we can plug in, move the negative sign to the right-hand side, right? We can plug in this for here, right? And we get that this is just negative omega y of 0, right? That term right there. Okay. And so we get here, right, the solution for omega x, right, in terms of the initial condition on omega x 0 and omega y of 0. Right? Likewise, right, for y, omega y, well, how do we get that? Well, again, we use that little substitution, omega y of t, just divide by negative lambda equals negative omega dot x of t over lambda, right? And we can just differentiate omega x, and we get this expression here. We plug in for omega dot x, and we get this expression here. We simplify that out for negative omega y of 0. It becomes positive, and so we get an expression for omega y and an expression for omega x. So we have a closed form solution for both omega y and omega x, which are, remember, right, here's your body fixed frame, right? Those are the components of omega in the body fixed frame, and the y and the x components. So if this is x and this is y, right, it's the distance in that direction and the distance in that, well, it looks like I've drawn it entirely in x, but you get the picture, right? So that's a component in the x direction. And, right, you can see that it's changing with time, right, as determined by lambda t. And so it's going to have a period, or it's going to rotate through with a period of a lambda over 2 pi. Right? So when t equals, actually 2 pi over lambda. So when t equals 2 pi over lambda, right, we get back to 0. Or we get 2 pi. And sine of 2 pi is 0 again. Right. So we have a closed form solution for omega x and omega y, but they're changing with time. Well, that makes life a little bit complicated. So how do we predict the motion? So what we're going to be looking at is constants of motion, right? And so again, if I draw my little diagram here, in the body fixed frame, c omega, that's changing with time, right? The first constant we're going to look for, well, we know omega z is constant. And the second thing we're going to be looking for is the component of omega, right? The distance of omega from the z-axis. The distance of this omega vector from the z-axis. And we're going to show that's constant, basically. Okay. So let's define, well, what is that, right? Well, it's just triangle rule, right? It's just a Pythagorean theorem, square root of omega x squared plus omega y squared, right? And then we know precisely what those two terms are, right? So we can just plug them in. There's one. And there's the other. There's omega y squared and omega x squared. So we just plug those in from our formula. Expand this out, right? So we get a sine squared term, the cosine squared term, the two cross products over there, and then so this big thing, right, comes from here, and then the second big thing, right, do the same for the second term, right? Well, I should maybe make it a different color. Right, that comes from this, right? So we expand those two out, and we notice that this term cancels that term. Right? They're the same term, except there's a plus and a minus sign, so those terms cancel out. We just cross those out. And we add the remaining terms back together again, right? And we get a cosine squared, the coefficient omega x naught squared, sine squared plus a cosine squared term, right? So that goes there, that goes there. And likewise with the omega y coefficient, right? We get this term goes down here, this term goes down there. And so what we know, if we know anything, is that you add sine squared and cosine squared is equal to 1. Right? And so those 1's here drop out, and we just get the omega x y squared term is the initial condition, basically, of omega x squared and omega y squared. So it's a constant. Yeah. So there's an invariant motion, right? The distance of this angular velocity vector from the z-axis is going to be a constant. The distance from the z-axis in the body fixed frame is a constant. That's pretty important. Right? So it's not, right, the vector itself is going to be rotating around, doing its thing, but the distance from the z-axis will remain fixed. Right. That type of motion, right, the rotation of the omega vector is often called precession. Now, precession, nutation, right, these sort of get mixed up in analytical mechanics in various places. But in our terms, satellite dynamics, this is precession. That's fairly standard. But we also call it nutation sometimes, and that is mixed up because nutation is usually actually some kind of motion about that. And that's the case when we have torque. But again, we're not going to consider that. So just be careful when you're talking about nutation. So yes and no. So is that the same thing? Yes and no. Depends on who you ask. Right? If you ask a satellite person, they might say yes. If you ask an analytical mechanics person, they might say no. Okay. So basically, what this is you got the body fixed z-axis here, right? And your angular velocity vector is rotating around it, right, at an angular velocity of lambda, right? Notice that if lambda is positive, it's going to rotate in the counterclockwise direction. The rotation, it's about the z-axis, I should say. So it's counterclockwise if lambda is greater than 0, and clockwise if lambda is less than 0. And we'll talk about that in just a second. So it's basically just your rotation matrix all over again, where you're rotating your initial angular velocity vector in the body fixed frame about the z-axis at a rate lambda t, or at an angular velocity lambda. So the solution just comes down to, we did in the scalar version, as the rotation matrix of the initial angular velocity vector. Right. So now, as I said, right, positive lambda counterclockwise, negative lambda clockwise, right? So now let's talk a little bit about what positive and negative lambda mean. So what are positive and negative lambda? Well, first of all, we'll assume that omega z is positive. Right? Assume that omega z is positive. Right? Otherwise, all the stuff switches. But so we're assuming that our rotation, the component of rotation around the z-axis is counterclockwise. Right. So that's important to do. Make that assumption. So then we can look at the remaining terms. So, well, Ix is positive, right? So that's not going to change. The only thing that can possibly change sign is this, right? The Iz minus Ix thing. Ix minus Iz. Or Iz minus Ix, I should say. And so when is that positive? Well, that is positive when your moment of inertia about the z-axis is bigger than your moment of inertia about the x-axis. So what does that look like? And this is why we talk so much about some intuition into the angular momentum or angular moment of inertia tensor, right? So if this is your z-axis, right, and here's your x-axis, and this can, remember, ix equals iy, so it doesn't matter if it's y or x. Right. So your moment of inertia about the z-axis is if your mass is, there's more mass farther away than the z-axis than it is from the x or y-axis. Let's make that x. Right. So if we had a spacecraft that looked like that, like a disk, right, and it was oriented in this way, then there's more mass farther from the z-axis than there is from the x-axis. Right? So the extreme case where it would just be a ring, right? My drawing skills are now fading. Right? Extreme case where there's no mass at all close to the z-axis, and there's lots of mass close to the x-axis. Well, maybe not lots, but some. Right. So in this is the case. It has a particular name, and it's called oblate. Oblate. Right. Right. And do try and remember that name, oblate. Right. And that's the case when IZ is greater than IX. Most of the mass is far away from the z-axis. Right. The converse, right, is the prolate, right, motion. Now, okay, so let me just define prolate before I get into these terms. Right? So prolate, right, is when, right, your IZ minus IX is negative, right? And that's where the case where this is small and this is big. So that means that most of your mass is centered near the z-axis. Remember, it's axisymmetric. So that would be the case where you had like a pipe, right? A tube or something like that. Or a rocket, right? Let's maybe draw a rocket. Sounds more spacey. Right? Except I'm not very good at drawing rockets. There's a rocket. Z, and then X, right? So most of the mass is close to the z-axis, and there's quite a bit of mass far away from the x-axis, right? So this has another name, this type of geometry, and that's called prolate. Why prolate? Well, oblate, it's fairly obvious, it's like fat, right? It's like sort of fat away from the z-axis. And prolate, well, you can just think of it as thin, right? Thin versus fat. Remember, they have two axes of symmetry, right? So there's a natural fatness, right, far away from the rotational axis, and natural thinness as well. Okay. So there's a prolate and oblate, depending if you're fat or thin. Right. And so the natural question most people have at this point in the lecture is this going to be on the final? And the answer is yes. It's a little late in the lecture to be mentioning that. But yes, all of this will be, there will be an exam question on the final on this topic. Right? So do try and remember. Now, so what's the difference, right? So oblate case, your lambda is positive. So the oblate case, lambda is greater than 0. And the prolate case, lambda is less than 0. Right? So the rotation of the angular velocity vector in the body fixed frame of an oblate object is positive, counterclockwise. But I mentioned in the body fixed frame. And why do I emphasize that? Because, right, these terms here, which are sometimes used. So retrograde would seem to mean negative, right? Retro. And why is that? Well, that's because these velocity vectors are reversed when we look in the inertial frame. And so this is from the inertial perspective. But anyway, that's what it's called. And direct would seem to be positive, but again, that's in the inertial frame, and we're in the body fixed frame. Right. So just a little caveat right there. So definitions: oblate, fat, rotation positive in the body fixed frame, negative in the inertial frame. Prolate, rotation is positive in the negative in the body fixed frame, and it's called direct because it's somehow positive in the inertial frame. So I've got some little videos here just to illustrate. These are this is an oblate object, right? It looks oblate, right? It looks fat. And here you see this is actually the angular velocity vector, the black line in the this is in the inertial frame. Right? And here I've got on the contrary, I've got a prolate object, right? Classical prolate object, and then you have rotation again in the body. This is in the inertial frame. And so if you open the lecture, you can look at those. Right? So the again, the black arrow is the angular velocity vector, and these are in the inertial frame, right? Attached to the angular momentum vector. Right. So now we're going to try and do a little bit of translation between the inertial and the body fixed frame. And to do that, we're going to, define some more constants of motion. So how do we translate that angular velocity vector, right, back and forth? And so to do that, we're gonna pick up the angular momentum vector, right? Because remember, the angular momentum vector is fixed in the inertial frame, but not in the body fixed frame. So let's focus on that angular momentum vector and see if we can get some geometry. Right? So here's our angular momentum vector. Right? It's defined using the inertia tensor and the angular velocity vector. And so since these are naturally defined in the body frame, this is an expression for the angular momentum in the body fixed frame. And so it's relatively simple because we don't have any cross terms, right? We can just figure out, right? Just it's a diagonal matrix, and so we get a very simple expression for the angular momentum vector in the body fixed frame. Now these omega x and omega y will be changing, but this will not. H z is fixed. These change. So let's orient ourselves with respect to that angular momentum vector, right? So we're going to be focusing on these cones, these body cones and space cones. So these are cones. The body cone is fixed in the body, and the space cone is fixed in space. Right. So fixed in inertial space, but not in the body. Whereas the body cone is fixed in the body fixed axis, but not in space. Right. And the intersection of these two cones is where the angular velocity vector lies. Right? It lies at the intersection of these two cones. Right? And so we're going to spend a little bit of time, right, talking about the orientation of these two cones. So it's fairly clear the body fixed cone, right? Body fixed cone is tilted at an angle, right, gamma from the z-axis, right? So that's going to be determined by omega xy, right? Because remember, the component of omega perpendicular to the z-axis is fixed, right? Likewise, the space cone, right? So this is this h, right? That's going to define our z-axis in the inertial frame, right? And this is our z-axis in the body frame. The well, obviously we know what it is, right? And so the orientation now will show that the orientation of this angular velocity vector in the inertial cone with respect to h, right, can be determined, well, not just by this gamma, but by this other angle theta here. So we'll talk about that, derive that in a second. All right. So now x, y, and z are body fixed unit vectors, right? We can add a b to them if we like. And now we have an expression for the angular momentum vector, right? So there's remember from the previous slide, the component of the x, the y, and the z coordinate system. Now in our particular case, we have ix equals iy, so we'll just make that x, right? And then, right, we can group these two terms together here, right? But we can't group this term together, and so this is a little bit tricky. So what we're going to actually do is add and subtract the ix omega z component here, right? So we're going to add it here, right? Ix, right? And subtract it here, right? It's just arbitrary, add and subtract. So those two cancel each other out. Right, so we have to get the same thing, but now this is convenient because this term, right, is just the angular velocity vector, again, in the body fixed frame, right, multiplied by ix. So that's we get some relationship between the angular momentum vector, right, body fixed frame, and the angular velocity vector in the body fixed frame. And now we have this other component, which is constant, and which is in the z hat direction, in the body fixed frame. Right. So, right, now we can expand this out and solve for omega, right? Divide by omega ix, and we get an expression for omega in terms of, right, the angular momentum vector and the z hat component. Right? So this means that our angular velocity vector at all times, right, is going to be a combination, a linear combination of the angular momentum vector and the z hat component, which is, the z hat coordinate, which is fixed, right? So what this indicates is that the angular velocity vector, right, is in the plane defined by the angular momentum vector, right, and the angular velocity vector, which means that, right, we knew that this was at a constant angle from from the z-axis. And now what we know is that the angular momentum vector is somewhere, well, it doesn't necessarily need to be between. It could be over here as well, right? But it's in this line, right? It's at some angle from the angular velocity vector. We don't know what that angle is yet. So, but it's in the plane. Yeah. So now we're going to try and figure out the angle that the angular momentum vector makes with this. We know it's in the plane now. Now we're going to try and figure out what this angle here is between these two. Well, we're actually going to go at a slightly different tangent. We're going to try and figure out what the angle angular momentum vector makes with the body fixed z-axis. That's what we're going to try and do. So how are we going to do that? Well, we know what the angular momentum vector is, right? We already figured that out. It's in the body fixed frame. And so that angle that I just described to you, right? We can use the definition of tangent, right? We're going to break that angle down, right, into the omega z component and that omega xy component, which we already determined was constant. So what that indicates to us, right, is because both of these are constant, right, that the angle that the angular momentum vector makes with the z-axis is also constant, and so we can actually figure it out, right? So let's try and figure it out. So we got the omega x, omega y squared, x and y squared components. We know what those are, right? That's hx, that's hy, that's hz. And so we can just solve for this angle plugging in to those components. Those x and y are the same, so we pull out the x component, and we get ix times, right, omega x squared plus omega y squared, which we know is, right, omega z, a constant. And the denominator doesn't change at all. Okay. So that the angle that the angular momentum vector makes with the z-axis is fixed, and it's given by this expression here. Okay. So that tells us something, right? And of course, we already know what the gamma. We already know the gamma. The gamma is even easier, right? That's the angle that the angular velocity vector makes with the z-axis, right? And that's just the omega, right? Omega z, the omega xy component, and omega z component, right? And so again, we use that definition of tangent, and we know that that's a constant, and so that we already knew that angle will be constant, but now we have an expression for it. And furthermore, right, what's interesting is that if we look at the expression for theta, the angular momentum angle, part of that is just this expression here. Right? So we plug in that expression there. We know that's equal to tangent of gamma, and so we should express theta, right, as in terms of a tangent gamma, right? So with this, this is interesting, right? What it tells us is that the relative magnitude of theta and gamma. If it tells us if theta is going to be larger or smaller than gamma. And now in this picture, right, an oblate object, we have theta less than gamma. By contrast, right, it didn't need to be so, right? In a prolate object, there's our prolate object, sorry. There's omega, there's h, right? That would be gamma, and that would be theta. And in that case, we have theta greater than gamma, right? And so we can just look at this, right? If this is greater than 0, right? If this is greater than, not greater than 0, greater than 1, right? Then Ix is greater than Iz. And so theta, right, is going to be greater than gamma, right? So if Ix is greater than Iz, right? Ix is greater than Iz, then we have the case of a prolate object, right? Because the Iz in a prolate object is small, right? Small. therefore prolate. Whereas if z is big, therefore oblate. Right? So in an object, as we have illustrated here, right, the angle to the angular momentum vector is going to be smaller than the angle to the angular velocity vector, and vice versa in the prolate case. So this allows us to define our cones, right? Our space cones, right? In here we've got the orientation, right, of the body fixed z-axis with respect to the angular velocity vector and the angular momentum vector. So this is the z-axis, remember, in the inertial space. This is the z-axis in the body fixed frame, right? And what this says is that this angular velocity vector, right, is going to be rolling around the body cone in the body fixed frame and the space cone in the inertial frame. And because this angle is larger than this angle, right, the space cone is outside the body cone. Conversely, right, here again we've got the z hat inertial direction. Inertial. And the z hat body fixed. Because this angle is less than gamma, right, the space cone lies inside the body cone, right, and so it rolls around on the inside. I think I've said all this. We can extend this a little bit to talk about our Euler rotation rate angle. So what is the angular velocity of the map between coordinate systems? Right? So these are the Euler rotation rates, Euler rates. Right? So these are defined as how you get from the inertial frame, and here I've defined E hat z, right? We have some inertial coordinate system, and then we have E hat x and E hat y coordinates, right? And we have our body fixed frame over here. So x hat body and y hat body, right? So the Euler rotations, right, are a 3-1-3 rotation, which allows you to get from the inertial coordinate system to the body fixed coordinate system. And there's 3 of them, right? So it's a way of lining up these coordinate systems, and it corresponds to these cones that we see here. Right? So the first one, right, is a rotation about the angular momentum vector, right? And what that does is it lines up the this ex hat to be, well, I guess perpendicular is actually not really the right word. It lines it up to be, right, sort of in the same, so this is x hat body, right? It puts the E hat x coordinate in the x xz plane, right? So really not in x hat z hat plane. That's what it really does. Right? So that's the first Euler rotation. So that's about the z-axis. So that's a 3 rotation. The next is a 1 rotation, right? In this, so here we've got now our E hat x. No, I should put this E hat x. Sorry, it's a typo. So this is a rotation about the 1 vector. And what that does is it aligns now our z-axis with the body fixed z-axis. Right? So we've got here a actually, I was wrong about that. It is perpendicular, right, to the z-axis. So it this one actually, the first one rotates it the x-axis until it's perpendicular to the z plane, right? So it's now perpendicular, and now we rotate about the this E hat x direction, until our z coordinate right here, right, lines up with, right, so that's the, where is it, the theta, right, theta, until it lines up with the z coordinates. So I'm like making a bit of a mess here. Actually, we don't do much with y, so let's just get rid of y. Right. So it so the first rotation, right, puts e hat x perpendicular to the x hat z hat plane. We actually don't need that one very much either. Right. So perpendicular to that plane. Then we rotate about, and this is not a clockwise rotation, so I should go the other way. We rotate about the e hat x direction in the counterclockwise direction about an angle theta, which then aligns this e hat z direction with the z hat direction, right? Because we know that's fixed, right? It's a fixed angle theta, right? We know what that is. And so now the only thing we've got to do now is rotate our x coordinate back about the z hat x until it lines up with x hat b. Right? And so that's our third rotation, phi, right? So about this z coordinate, right? And which is lined up well with here, e hat z coordinate. And so we rotate this back, right, until it lines up with x hat b. Right? So the e hat x coordinate goes over here, perpendicular to the plane. We tilt the plane over until the z hat and the e hat z are aligned, and then we rotate it back, right, so it's lined up with the x hat b direction. Right. So those are Euler rotations. Now we can find an expression for those as a function of omega. So here's, right, omega, right, in terms of the e hat directions, and we can get that right from here. Right. So this is so if we know what the rates of change of these three things are, well, this one's 0, right? And we know what these are, right? They're the three rotations, right? So this is an x. This is the omega, or this is the Euler rotation. It's about x, about the z coordinate. Sorry. So it's like has only a component in the z. Well, I shouldn't say it's omega z, right? And this one only has a component about the 2 direction, and this one again is a 3 rotation. Actually, I think this one should be over there. But it's 0, so it doesn't matter. So I think that's a typo, right? I should double check it though. In any case, so because, right, this is in the first coordinate system, it gets 3 rotations. This is in the second coordinate system, it only gets 2 rotations. This is almost in the final coordinate system, it's the third coordinate system, so it only gets 1 rotation. So we apply these matrices to these rates, these Euler rates, and we get a simple expression given here. So this is what we saw on the previous slide. There's that theta dot. So, right, what's interesting, right, this is a constant, we know, right, because omega z is a constant. These, however, these are going to change, right, over time. Because these change over time. Those are Euler rates. We won't need them very much in this class, but it's worth talking about them. So we can actually express, right, the omega dots as a function of the Euler rates in the inertial coordinate system, right? And we can actually solve then, right, from the last one, right, to get an expression for the dynamics of these Euler rates in the inertial coordinate system, right? So again, they depend, right, on the relative fatness versus thinness, right? This is x as well. Actually, that looks like a typo. That should be z. Right, my bad. So if we have in this case, remember, Iz, this is a fat. This is large. Iz is large, so therefore fat. Therefore fat. This is the oblate case. Right. Then this term here will be negative, right? Less than 0 in the oblate case, and will be positive in the prolate case, right, where Iz is small. And that's why these are called direct versus retrograde. It's because the Euler rates in the inertial coordinate system are processing the opposite direction. So this the right, that rate, and right, that rate. So if these things need to rotate in opposite directions, that's the prolate case, and if they rotate in the same direction, that's the oblate case. And yes, again, right, here's the oblate case. So in this case, right, you rotate the first Euler angle, and you also rotate the third Euler angle in the same direction in order to get that match. Right? Actually, I think these are backwards. Right. So to illustrate, I've got like a nice little demonstration here in Mathematica, which someone put together. It wasn't me. But again, it's very nice. Let's see. Okay. I don't think I can make it any bigger, so I apologize for that. So this is right, we can move it around a bit, right? Here, just to orient us, the green, red, and blue dots are the axes, x, y, and z. In the body fixed frame, the red, green, and blue arrows are the x, y, and z axes. In the inertial frame, you can see that the z-axis in the body frame is obviously pointing towards the z-axis in the body. So this is a prolate object. This is a z. And here we don't have in the inertial frame doesn't seem to line up the angular momentum vectors. But the angular momentum vector, I believe, is the let's say we could just simulate and find out, is the gray vector. So the angular momentum vector is gray. The angular velocity vector is the black one. So this is in the inertial space, right? So the angular momentum vector is fixed. This space cone, which is this gray thing, is fixed. The intersection of the body cone, which is attached to the body, and the space cone is the angular velocity vector. So there's a prolate object, so the space cone is outside the body cone, so it's floating around outside there. And what else can you see? So you can see in the inertial space, right? Your angular velocity vector is rotating around like that, and your angular velocity vector is, it's a positive rotation. Switch to the body fixed cone, right? And here again, the gray vector is the angular momentum vector. It's now moving around because you're in a non-inertial coordinate system. The angular velocity vector is attached, right? It's moving in the opposite direction now. It's moving clockwise, right? So it's moving negatively. So the angular velocity vector and the angular momentum vector are both moving in the clockwise direction, so negative rotation. Whereas in the space inertial frame, the angular velocity vector is moving positive, right? So this is retrograde case. Or no, this is posigrade case. Right? Now, if we do the opposite, consider the opposite, we consider a fatter spacecraft. Let's make it a little less high. Right. Well, make that body kind of a little bit bigger. Maybe that's a little bit. Oh, okay. There we go. Let's see if I can get this oriented so we can see a little bit better, or not. Let's see. Stop. Maybe I can rotate. Yeah, there we go. Okay. Okay. So in this case, right, we've got an oblate object, and we see the this is the inertial frame, right? The gray vector is the angular momentum vector. It's fixed, right? And that angular velocity vector is rotating about the angular momentum vector, and it's doing so in a counterclockwise direction in the space cone, in the inertial frame. And the body fixed frame attached to the body, right, gives us that, tells us where the z-axis. So it's spinning a bit fast, so I guess it's like hard to see. Let's see if I can maybe slow it down a bit. Right, yeah, there it's a little bit better. Right, yeah, that's good. So here, hopefully you have a high-res monitor, or you're watching this in 4K. You can see that in the inertial space, right, that angular velocity vector is on the opposite side as the z-axis. The z-axis is precessing around counterclockwise, as is the angular velocity vector. Right. Here we go. So again, there's a link to this in the lecture notes if you want to download it. It's lots of fun to play with. You can watch it. There's the body fixed frame moving around relatively slowly. That space cone there, the angular momentum vector moving around. You can see the fixed angle between those two. Right. Let's go back now to the slides. We see again a couple movies, right? Here's the Prolate object, right? It's spinning around. This is in the inertial frame. Angular momentum vector fixed. You can't, of course, see where the angular velocity vector is, but it's somewhere there. And no. There we go. And finally, a very large. Can we mute that, please? Right. This is the asteroid Vesta, right? It is rotating, right? Not very fast. It's an oblate object, and you can see it precessing there a little bit. Right? That angular velocity spin axis is moving around in time. Again, you can watch these in more depth on if you get the lecture notes from the website. All right, so almost done now. Just a couple mentions. Some people call nutation, right? Precession. Some mix them up. Other more common is the nutation. Is this variation about that angular velocity vector? So the angular velocity vector actually moves not smoothly. I believe that the gamma angle changes a little bit, and that's in the case where you have torque. Right? We don't have torque yet in this lecture. A good numerical example of this, right, is the Earth. Now, the Earth is, remember, an oblate object because it's a little bit fatter than it is tall. Right? So the Earth is oblate. Now, I've got these like numbers switched, so because I pulled this off the web, I forget where. So you don't get confused there. So the Earth is roughly 42 kilometers wider than it is tall, right? So there's an extra 42 kilometers. Well, it's divided by that, so 21 kilometers. A little fatter, 21 kilometers. And so you would think, well, the Earth is rotating about its axis, and its axis is maybe a little bit tilted, so that the Earth itself would, have a little axisymmetric action there. So it's axisymmetric, right? It's an ellipsoid, meaning sort of a three-dimensional ellipse. And we can calculate the moments of inertia for an ellipsoid, right? So the Ix and Iy are the same, and they're both equal to this, right? Here's the width, right? And the Iz axis, right, is just the width, right? Doesn't matter how tall it is. The height. Right. So in our case, right, the width is bigger than the height, right? So that they're not the same. Ix does not equal Iy, does not equal Iz. So we can calculate Iz. We can calculate Ix equals Iy, and they're slightly different, right? 0.04 difference. So, but that's enough. That's enough that we can calculate the nutation rate. And so we can do so. We can plug it into our formula for this nutation rate. So this bit is 0.04, and this bit is about 10, right? And we calculate around that when we do that, we just add a little decimal point right there, and we can get a rough estimate for the precession rate of the Earth, right? 0.004 radians per day. We can from that compute the period of the rotation, right? Which comes out to be about 243 days. So does the Earth actually nutate? It turns out it does, right? And it's been measured. It has its own name called the Chandler wobble, right? And then, of course, the next question is, does it match our predictions, right? Torque-free motion. There is actually torque in this system from the ecliptic, but we're not going to pay attention to it. So if we plug that in, actually, if we use the actual values of the moment of the inertia tensor for the Earth, they're actually slightly different than what we calculate from the previous slide. And so let's go with those. In this case, it doesn't change much, right? The difference is still 0.035 or thereabouts, 34, 33, something like that difference. The magnitude changes a little bit. It's 8 as opposed to 10, but we can calculate that about. And so that if we do that, the nutation rate slightly. So that's lambda. And so t, we calculate 2 pi over lambda. We get that's equal to 306 days. So using the actual numbers. And then how does that compare with the actual wobble of the Earth? Well, we can calculate that as well. I got it from somewhere on the internet that the actual wobble is 434 days. Maybe. And here actually we've got some data calculating the rotation angle of the Earth, right? And it starts here, right, and ends here. So it starts in 2005, ends in 2013. So that's period. We got about 8.3 years going on there. And how many rotations does it get through in that time? Well, let's see. How many times does it cross? So from here, our first crossing goes 1, 2, 3, 4, 5, 6, 7. About 7 and 7.5 rotations. Just based on this sketch. So 7 rotations in 8.5 years. So that looks about, it's a little bit more than a year. So about 434 days. So sure, why not? So doesn't match the prediction perfectly, but there's various reasons for that. The things inside the Earth aren't rotating quite the same way as the Earth. There's lots of sort of things going on that are a little bit more complicated, but that's what it is. So primarily, Earth is not a rigid body. That's the error, right? Not a rigid body. The molten core is not rotating exactly like a rigid body, and so if you do it accurately, right, you can get the right number. But our rough and ready approximations are good enough for us. This was noticed a long time ago, of course. Euler and Lagrange. I don't know if Euler and Lagrange and D'Alembert would have calculated analytically, but I believe that it was originally noticed back in those days. That would be like early 1800s. The magnitude of the rotation is not great. It's about 9 meters, but we can still measure it. Here's actually the actual motion in arc seconds. The previous one was milli-arc seconds. And you see it increases and decreases, and that's because of nutation. So small, large, small. So the magnitude of that angle varies over time, unlike the perfect rigid body torque-free motion. Okay. So that brings us to the end of the section on axisymmetric. In the next lecture, we'll cover what else? Non-axisymmetric motion, right? In that case, the equations of motion, we have 3 equations of motion. Things become a little bit more complicated. We're going to have to linearize, right? We can't, right? Because we don't have omega z equals constant. Not equal to constant. And so the motion is nonlinear dynamics. And so what do? When we have nonlinear dynamics, we linearize them. And we'll look at the stability. Very interesting little demonstrations you can do with a non-axisymmetric case. And then we'll talk about the problem of fuel sloshing and why Explorer 1 failed and why all of our satellites that we have now are all oblate and none of them are prolate. But we'll, again, cover that in the next lecture.